And then some. All right, guys, well, welcome. I think it's 4 o'clock. I told the math department they need to get a battery up here to this clock, so maybe by next week it'll be fixed in time for our exam. We'll see. Welcome. I hope that you guys are hanging in there. I know this is the crunch time, the final stretch, and that can be a little bit nerve-wracking, a lot going on. I do, however, at least as a bare minimum, I have a little bit of good news for you guys today. We met the 85% mark. I just checked it right before class, and more than 85% of you have filled out an SOQ for me. So I really appreciate it. That means that you all get another extra 2 points towards this midterm that we're going to take next week. So a lot of you have got 2 points for that. You've hopefully got 2 points for the video on annihilators that you watched about a week ago. And did you all read your email since last class? There is an extra credit quiz. I decided to put that in front of the homework assignment because we have not covered 9.5 until today. And I didn't want everybody just sitting around not getting that done. It's not a very long quiz to do. If you haven't done it yet, you have time still. It is due tonight at midnight, and there are 3 problems on it, and they're each worth 1 point. And really, it's just to get you to start practicing for our exam that's coming up next week. So anyway, so all of you have the 2 points for the SOQs. Most of you have 2 more points for those videos, and you can get another 3 points by doing this extra credit quiz. My goodness, I'm getting soft in my old age. That's 7 points that you could end up with even before you start on the exam. So don't forget about that though, because I just checked, only 12 people have turned in the extra credit quiz, and there's a lot more than 12 people here. So that just means some of you still need to work on. I know I just passed it out a short while ago, but still, I know it's a short turnaround time, but it's also something that I know should not take very long to do. So please try and do that if you want those extra credit points by midnight tonight. I'm going to grade them as soon as I can. The very next thing after that will be homework 23, which is essentially the last homework for the semester. There will be a homework 24 next week, but it only has 2 questions on it, and it'll be really quick. So this is really the last major assignment of the semester, and it will be due on Saturday. Now, we don't have class again between now and then, so we're going to have to rely on office hours a little bit to get help with any of these problems. So I will be adding some office hours, and I'm sorry I haven't quite figured out. As usual, I'm trying to go hiking one day this weekend. I don't know when it's going to be. It's just my personal thing. Once I figure out when I'm going to be available, I will send an email to let you know. But I will make sure that I have some office hours for you before you have to turn in this homework number 23. Okay. Our midterm is our very next class. So when we come in here next Tuesday, hopefully everybody's going to be on time so that you have the full 2 hours to work on this exam. Here I reminded you what sections is going to be covered. And maybe while I'm at it, I'm going to pull the screen down in front of it because I did put this up on this computer for a second just to show you, as usual, that there is a folder here in Canvas. And it is just called 3rd midterm resources. Okay, so if you click into there, this should be by now something you're pretty familiar with. We have 2 sample midterms. One of them is the all caps version. One of them is the all lowercase version. So you have 2 sample exams to practice on. As always, my advice is everybody should at least, at bare minimum, do one of those. Okay. And then if you have more time, or maybe you do one of them and you see that you have some things you need to work on, then you can go to some of the other things in the packet. So there's a review session. So on the review session, I wrote out the questions and the answers in detail. So if you want the fast Reader's Digest version of how to do those problems, you can just read that. But if you like listening to my voice, the sound of my voice keeps you going, you can do that also, because in the pages section, so if you go over here to pages, there is a link to something that's called review session for midterm 3, and it's a 3-hour video. So that's something that you would have to invest a little more time into. But if you have the time, and if you realize that you're not quite getting it as well as you would like so far, well, then that's definitely something you could do if you have the time. So there's a review session there. There's also just a review packet that has an overview of all the terminology, the bullet point list of the things to be able to do, and so on. There's also some practice problems in the review packet. Some of those, again, some of those are pretty old. I wrote them in there like 15 years ago or something, and I look at them now and I'm like, this isn't quite the way I pitch the material these days. So if you start looking at some of those, you might feel the question, some of those, not all of them, but some of those questions might just look a little weird to you. They're not bad questions. They're just, maybe not framed the way that I've been doing it in more recent times. But you can certainly look at those. And then if you've done all that and you tried one of the sample tests and you still have more time, you could try the other one and go from there. So there's more than enough for you to do here. Obviously, I just wanted to remind you again that that really should be the basis of your studying. Not so much just trying to redo all the homeworks. It's just too much to redo all the homeworks. I will mention, so the homeworks that are relevant for this exam will be 15 through 23. That's quite a bit of homework. I don't think anybody's going to go back to all of that again. If you did get red penned on one of those assignments or something a little bit heavy, well, sure, maybe you want to go back and look at something kind of specific that was a weakness for you. That's totally fine. But I wouldn't try to redo all these homeworks. I would prefer to see you go to the resources folder and work on that instead. The group works that are relevant for this exam start with number 10 and they go through 15, but I have to warn you, we're probably not going to do 15 together. We've done 10 through 14 already, but I have a lot to cover today and I'm probably not going to do group work 15. So that'll be just for you on your own to look at if you want to. Okay, so that's kind of what's going on. And I mentioned on Tuesday that, if you can really make a strong effort towards this midterm, it should help you a little bit as we get closer to the final. Okay, I am going to say one quick word about the final right now, just so you can put it on your radar. I don't want you to get confused between the midterm and the final. Our final is scheduled for the following Tuesday, which is May 13th from 5 to 7. So the first thing I wanted to say is I'm probably going to let you work late on this. So I'm not going to kick anybody out at 7. I would probably let you keep going. Just so you have plenty of time. I mean, I'm going to write the exam. So if somebody knows what they're doing and can get right into it, sure, 2 hours should be plenty. But I'm not going to put that pressure on you. I would not, all I'm trying to say is I would not schedule your, date of a lifetime for 7:15 on Tuesday, right? Give yourself a little cushion of time just so you have a chance to stay a little extra if you want to. The other thing I'm going to mention is that, as you guys know, I have another section of this class. My other section is taking the final on Thursday from 5 to 7. Well, it turns out, I know this because I've been around a while, that during finals week, this place is pretty much wide open. Like you can hear a pin drop in this building. There's nobody around. So I thought, what would happen if I reserved a second room? So I did that. I reserved a second room on both the time of your final and at the time of my other class's final, so that you can choose which time you want to come. So depending on when your finals are, if it would be better for you, if you want to, you can come take my final on Thursday instead of Tuesday. I would be careful with that because obviously you have other classes you have to balance against. But if you think that that would be better for your schedule, you can do it. And the reason I say that having a second room, if everybody decided to show up on Thursday, you're not all going to fit in this room because that's 2 sections worth of students can't fit in one room. So I reserved 2 rooms, this being one of them, and I reserved them from 5 until 8. The two finals will be equivalent. I will probably write two different finals, however, just so you're aware of that, because it's too much time in between. But they will be equivalent finals. So you can make the choice. You don't have to tell me ahead of time. If you, if it's 4:45 on Tuesday and you're like, I'm not ready for this thing yet, and you're free to study for 2 more days, you can do that. It's just totally up to you. So you can just show up at whatever time you would like. Any questions about, that's for the final, that's not for the midterm. This place is too busy during the regular weeks to get 2 rooms. Joe?
Where's the second class?
I'm sorry?
Like, where would it be, like this class or next one class?
Yeah, I reserve a room that I can sprint between in like 5 seconds or less. Yeah, so it'll be real close by, but everybody would come here, like you would know that this is the base, home base. And then I'll set up and I have another room just right down the hall. And I would take, if there was an overflow. I mean, it's hard to, I've done this before. Usually not very many people switch to a different time because they've already got it set up in their mind. But I just wanted to give you the option. I have no, I might as well make your life as easy as I can with respect to scheduling. So that's just up to you. Yeah. Any other questions? But first things first, we have the midterm, and for the midterm, we do need to do it during this class because I can't get a second room during a regular week around here, and at least not a room that's anywhere close. So I'm going to leave that as our usual game plan. Okay, well, believe it or not, guys, this is really our last full big lecture day. Next week on Tuesday, we have the midterm. On Thursday next week, we will be mostly reviewing for the final. I will cover one more section, which is what that last homework assignment that's got 2 questions on it will be covering. But it's a short section. It only takes maybe 35, 40 minutes to go over that. So next Thursday, we'll be reviewing for the final mostly. So today is really the last big push that we need to make, but it is a pretty heavy section. So we're going to have to really focus in today on what will end up being section 9.5. By the way, so you can see all the sections covered on the exam. It will include what we're going to do right now, which is section 9.5, which is what homework 23 is covering. So I'm sorry for the short turnaround on this, but we've just got to get it done. There's just no other way about it. So let me just set the stage for this conversation a little bit. We are trying to solve, as we've written down for 2 or 3 classes in a row now, x prime equals a times x. And we're hoping to solve that for x. X is the unknown vector. And we've already discussed this in pretty good depth, that we can make solutions of the form e to the lambda t times v every time we have an eigenvalue eigenvector pair of the matrix. So A is an n by n matrix. And as long as I have eigenvalue eigenvector pairs, I can build these solutions. And as long as my matrix is non-defective, this is what we talked about on Tuesday. If the matrix is non-defective, we can just write down the general solution here, which is made up out of C1 times e to the lambda 1 t v1, right? That's the first term. And then there's another solution with C2 corresponding to e to the lambda 2 t v2, and so on. And we would get n of those terms because the solutions form an n-dimensional vector space. Okay, so I'm talking a little fast. We, of course, did this all before. I'm just reminding you here. Don't forget, though, as we discussed on Tuesday, that it is possible that the eigenvalues and eigenvectors could have complex numbers in them. And if that should happen, then we have to actually take these e to the lambda t times v expressions and Floy them out. Do you remember that? The Floy thing we talked about on Tuesday. So in that case, it would look a little bit more expanded out than this, right? I'm making it look so small here. But if the expressions involve the imaginary numbers, then if you remember from Tuesday, we're going to get sines and cosines. We're going to get, a real piece and an imaginary piece. And we kind of have to like do that whole Floy thing. Did anybody have any questions about that? The Floy process so far? Probably not. I mean, when you do the homework for Saturday, you of course are gonna see that in there. And it'll be a good chance to practice on it a little bit. But it's not hard. It's just, we have to practice it a couple times. If you do the sample midterms and you do the homework for Saturday, by the end of all that, you will have done Floyd a few times on your own. And that will be good. If you feel good by the end of that, I think you should be ready to go for Tuesday on that topic. Okay. So this is just a summary of kind of where we left off. Everybody all right with this? Actually, to be honest with you, the hardest part of it is the stuff from chapter 7, where you have to come up with the eigenvalues and eigenvectors. Once you find your eigenpairs, writing this down is kind of just rubber stamp it down. Write it. You don't have to do any more calculations. You're literally just taking the information that you would have learned how to do 2 chapters ago, and you're just organizing it into this general solution. So the main work is actually stuff that we learned how to do a while ago. Yeah. Okay. Well, what I want to talk about now, though, guys, I've been hinting at this already, is what if the matrix A, which is my n by n matrix, what if it is defective? What if it is defective? So if it's non-defective, we're already good to go. But now, what if the matrix is actually defective? So maybe just to help us with this, I'll write down an example where that situation comes up. So this is section 9.5. And so this is where A is defective. That's what we're going to be talking about primarily today, the case where A is defective. So as an example, suppose I ask you to solve x prime equals, and then I'll put my matrix here, 0, -2, and then 2 and 4 times x. You take this as our example. And so obviously the matrix that we're talking about for capital A is the 2 by 2 matrix that I just wrote down right here. Okay, so start off with an example to sort of see how this is going to play out. And let me just kind of go through the motions of how we usually solve this, and then we'll see when we get stuck. At some point, we're going to get a little stuck on this. So the first step is to find the eigenvalues, and that means we take the characteristic equation. So this is a good review for next Tuesday as well, right? The determinant of A minus lambda I, we subtract lambda from the main diagonal of all of the entries. Okay, so you would get this matrix here, it's 2 by 2, and you can do your AD minus BC thing here. So we'll have negative lambda times 4 minus lambda, and then I'm going to have a plus 4 tacked on to the end of that. And if I just go ahead and I'm going to multiply this all the way out, I have lambda squared minus 4 lambda, and then plus 4. And I'll factor that now. And this one actually does easily factor. That's kind of nice, which is lambda minus 2 quantity squared. And what we're doing now, as usual, is setting that equal to 0. So we take that characteristic equation and we set it equal to 0. And as you can see, we get the lambda value of 2 repeated twice. Okay, so here we have lambda equals 2 and 2. Do I know yet whether this matrix is defective or not? I do not. I think it's tempting. Students, they see the repeat lambdas and they want to say, oh, it's going to be defective. Well, actually, it's not necessarily defective, because this eigenvalue could manage to pull its weight. We don't know that unless we calculate the eigenvectors by doing our null space calculation. Yeah. So I'm going to go here and set up a null space for this one. And the null space is obtained by subtracting 2 from the main diagonal of the original matrix. So we get -2, -2, and then on the second row, we get 2 and 2. Okay, so I've just simply subtracted 2 from the main diagonal of A. This matrix, as we've said 5,000 times, cannot be invertible. because the determinant had been set equal to 0 to get this matrix. So we know that if we did the EROs, we would have to be able to cross something off. We would get a row of zeros somewhere. And in this case, it doesn't matter. For a 2 by 2, you can cross off whichever row you want. I'll just get rid of the row that has the negatives on it. And I'm left with just this simple little vector here. And if we want, we could, I'll go ahead and do an ERO. I'll just put the 2, 2 up on top as a 1 and a 1. I don't think there's any harm in doing that. And from here, you can very easily find your eigenvector. We could use the AB trick, where we swap the two numbers and put a minus sign on one of them. That would give me -1 and 1. If you don't like that, you don't have to use the AB trick. You can just set up y as a free variable, and then that would be t. And then when you solve for x, you would get -t. As soon as you bust that t out, this is what you're going to have. Okay, so it's the same thing either way. But I now do know that the matrix is defective, because the eigenvalue has a weight of 2. It's listed here twice and only gave me 1 eigenvector, right? It's not pulling its weight. So this is a defective matrix. I mean, I can and I will at least write down one solution here, and using this approach. So I do have one eigenpair that I can work with here, and it would look, in this case, it would be e to the 2t times the vector -1, 1. I'm gonna go ahead and put a box around that so I can find it again later. But that's the only solution that I can get so far using the eigenvalue-eigenvector pairs, because I only got one of them. I only got one pair. But we know that for a 2 by 2 system, we must have 2 linearly independent solutions. And I've only given you one of them. So the question becomes, how do we get x2 of t in this case? This is the issue. When our matrix is defective, how do we come up with a second solution? This is what we're going to be talking about. So turns out that, well, I'll give you the answer. Oh, I hate this answer. The answer is that we are going to guess the solution again. Remember how we've done this a few times? I keep saying it's so good I have my PhD so I can guess the answer. I feel like I used my 6 years of education to 6 extra years to be able to guess a trial solution. So we are going to quote unquote guess a trial solution, and you are going to need to know this expression that I'm going to give you right here. We are going to guess a trial solution, and here's what it's going to look like, guys. x2 of t, the guess that we're going to use. Now, the guess that you might be expecting is, if you were paying attention last chapter, you remember that when we had repeated roots of our auxiliary equation, we did something called x stacking. We would stack x's in front of whatever we had before. In this case, of course, it wouldn't be x's, it would be t's, because t is now my variable. So you might think that we're going to just stack t's in front of whatever the original solution was. Turns out that's not what we need to do here. It's not, that will not work. What we actually have to do is a slightly more complicated thing. I am going to have my e to the lambda t there, but then what I'm going to have for the vector part is something, and by the way, this is not the notation in the book. So you will, if you are not normally one to take notes, today might be a good day to do it. We are going to put our x2 in this form, e to the lambda t times w1 plus t times w2. So there is a bit of a stacking of a t here, but there's also kind of a term that does not have the t on it. Okay, and what I'm going to say here, guys, is where W1 and W2 is to be determined. Where W1 and W2 is to be determined. So I'm going to show you now how to determine W1 and W2. Okay? And this is where the whole lecture really leads into is how to get the W1 and W2. As soon as we know how to do that, we can write down our second solution, and therefore we can make our general solution out of the two solutions that we come up with. So it's just a matter of me explaining this one little point. How do we find W1 and W2? Okay, well, what will happen is that they will be determined, they will be determined as soon as we plug our guess back into our original differential equation. This was our original, this is the equation of the whole chapter 9 that everything's boiling down to. So guys, right now, I am going to take the derivative of that x2 and set it equal to a times x2. I'm going to do the left side, I'm going to do the right side, I'm going to make them equal to each other, right? So let me just kind of write this down. X2 prime equals a times x2. This is really what we would have to be looking at. So let's do them one at a time. I'm going to start with the left side, guys. The left side tells me to take the derivative of x2. Now this is the derivative with respect to t. If you want to be really explicit, it's a derivative with respect to t. So I see t's in two places here, and there is a multiplication in between them, which means that to take the derivative, I have to use the product rule. Yeah, this is the product rule. This is a product of two terms. So it's going to be what? The derivative of the first term, that would be lambda e to the lambda t times the second term plus the first term, which is e to the lambda t, times the derivative of the second term. The derivative of the second term, let's see, the derivative of a constant is 0, and the derivative of t times something is just something, which would be W2. So put W2 right there. Okay, so that goes on the left side. This is, so if you're wondering where this is coming from, this is the product rule. So we just did the product rule to calculate that derivative right there on the left side. Ultimately, guys, you won't need to know this derivation, but I'm happy to see, you should take notes on it anyway, because who knows? You may want to remember how this is true or in the future understand it a little bit better. The right side, I have a times x2, which is e to the lambda t times w1 plus t times w2. And I am going to go to town doing algebra on that. The first thing I'm going to point out, guys, is every single term on both sides of the equation has e to the lambda t in it. So I'm going to cancel all of those. I'll cancel here and here and here. All of those guys can go away. Now, when I look at what's left now, I see that some of the terms have t's in front of them, and some of the terms do not. I'm going to consider them separately. It's kind of like, you remember when we had the problem on annihilators where there was like a cosine coefficient and a sine coefficient, and we sort of said, oh, the cosine coefficients have to line up and the sine coefficients have to line up. It's like that here too. The terms that have t's with them have to balance on both sides of the equal sign. And the terms that don't have t's also have to balance. So guys, let's do the t terms. So I'm going to kind of do two lines here. I'm going to do the t terms, and then I'm going to do the non-t terms on both sides of the equation. The t terms on the left side, the only place I have a t now is right here. And what is it being multiplied with? I have a lambda. I've already canceled the exponential, right? So I just have a lambda and a W2. So this would be a lambda and a W2. And that's the only place I have a t on the left side. On the right side, the only place I have a t is right here. And what is it being multiplied with? A W2. So the t terms have to match up. Lambda W2 has to equal A times W2. Right? Now let's do the non-t terms. Everything that has no t with it whatsoever, right? On the left side, where are my non-t terms? I have a lambda W1. Let's write it down, lambda W1. And then I also have this W2 here. So I'm gonna go plus W2. And then on the other side of the equation, the non-t term is A W1. Are you with me there? So again, I've canceled these e's completely. Let me actually erase them so they don't get in the way. And I'm just thinking, I'm just looking at the left side, I'm looking at the right side, where are the things that have t's on them and where are the things that don't? And in one equation, I put all the t stuff. And in the other equation, I put all of the non-t stuff. Is anybody with me? A little bit? This is the way the derivation goes. By the way, this first equation, does that ring any bells for anybody? A W2 equals lambda W2. Now be careful. Can I cancel a vector from this equation? Oh. Like, this gets out my red pen really fast. So you cancel the W2, then I have A equals lambda. And you don't, maybe that's when I go back for more pizza. Anyway, I have to take a break when I see that. A matrix cannot be equal to a number. I cannot cancel that, right? But does the equation itself look familiar? I am going to do a subtraction in just a minute, but does anybody remember, since we have an exam on Tuesday covering chapter 7, does anybody remember what the most important equation in chapter 7 was?
Was that eigenvector?
Yeah, what's the eigenvalue eigenvector equation? A, no, not A minus lambda I. A times V equals
Lambda V.
lambda
V.
V. Yes. I promise you that's going to be on the test next week. It's the most important equation in chapter 7. AV equals lambda V. Guys, that's what this looks like. Except it's got W2 instead. A W2 equals lambda W2. That actually means that lambda and W2 is an eigenvalue eigenvector pair. It really does mean that, right? Now, I am going to do what was suggested, somebody suggested a moment ago, which is we can subtract everything to one side of the equation and make it equals 0 here. And when I do that, remember that you have to stick this identity matrix in here on the lambda. So I'm going to write it as A minus lambda I times W2 equals 0. So just to remind you, I is just my identity matrix. So if you were to actually expand this out, you would have A W2 minus lambda W2 equals 0. It's literally the same as this. Okay? And the point that I was making a moment ago is that W2 is an eigenvector of A. Let's make sure we're not all getting too lost on this. What is this whole whiteboard all about? I'm trying to do the TBD part, guys. I'm trying to figure out what are W1 and W2. I've got some good information so far. I know that W2 is an eigenvector of A. That's helpful. That is helpful. What about W1? The W1 does not appear in the T terms balance equation, but if we look at the non-T terms, I do see W1 there, and I am going to rearrange this equation as well. I'm going to subtract the lambda W1 over to the side that has the A on it, so that I can write this as A minus lambda I times W1 equals W2. Okay, does everybody see that? If you solve this for W2, you would get A W1 minus lambda W1. And that's what we have right here. A W1 minus lambda W1. I stick that identity matrix in there to make sure that it actually makes sense. You with me? So you cannot just choose W1 and W2 independently. And in fact, if you tell me what your W1 is, then you do not get to control what W2 is. You must live with what W2 is based out of this equation. So I am going to just give you a brief information that there is a word here. We call W1, this is what is called a generalized eigenvector. It's not really an eigenvector, it's a generalized eigenvector, and I'm going to show you in what sense I mean that here in just a second. You might see this word from time to time. You'll see that word a lot more when you switch your major to math and take a Math 307 next year. You will see they talk lots and lots about generalized eigenvectors, but we're not going to do that. What I am going to do though, I find these equations a little hard to remember. So I found the perfect diagram to help us remember this, and it's not in the book. So you will want to write this down. But here is the way you're now I'm ready to explain how are you going to determine W1 and W2. You are going to end up, right, I'm going to draw a dot, I'm going to label it with W1, and you are going to choose W1. Now remember, as soon as you choose W1, you do not get to choose W2. You have to live with W2, which is calculated out of this, right? You take A minus lambda I, multiply it by W1, whatever that is W2. But here's the thing. I'm going to draw a little diagram with an arc on it, and I'm going to label this arc with A minus lambda I. Now, whenever I see an arc that has an A minus lambda I on it, what that's going to remind me is that I need to multiply the dot on the left by A minus lambda I, and it leads me to W2. This is just a picture that I like to use to remember this. But then guys, there's also a picture for this. Starting from W2, if I multiply again by A minus lambda I end up at, oh, this should have an arrow on it. I should end up at the 0 vector. Right? So if you understand this diagram, you are in good shape. The thing about it is though, you don't get to just choose W1 willy-nilly. No, you don't, because you need to make sure that W1 is not going to survive 2 powers of A minus lambda I. Every time I go across an arc, I am multiplying by A minus lambda I, and according to that diagram, if I do it twice, I have to get to 0, right? So in this diagram, right, so let me actually just make the explanation in this box, right? We're going to choose W1 so that 2 things are true. First, when I take A minus lambda I squared of W1, see guys, when I square the matrix, that's like doing 2 arcs of my diagram, and I have to get 0. All right, so you have to choose W1 so that when you apply the square of A minus lambda I to it, it gets killed. However, guys, you do not want the first power of A minus lambda I times W to already be 0. You do not want it to already be 0 because, guys, if A minus lambda I times W1 was already 0, that would mean that your W2 was 0. And if your W2 is 0, let's come back over here. If your W2 was already 0, then what was your second solution? It's really just e to the lambda t times W1, and W1 would have just been an eigenvector. Do you notice how if you have an eigenvector like W2, when you hit it with this A minus lambda I matrix, it becomes 0. I don't want W1 to be an eigenvector, otherwise I'm literally just reproducing the one and only original solution we had come up with before. I'm not getting a new solution. So that's the prescription. That's how we do it. And if it makes more sense, probably after we do an example, hopefully we'll be in good shape. Okay, so I'm gonna go back to my example now. I am partway through this example that was on the board. I wanna finish it now using what we've just discussed. Are there any questions so far, gang? We probably need to just see this example. So now let's go back to our example. Back to our example. I've got the form of x2 right here. I just need to figure out W1 and W2, and I've now explained what the prescription is. So I have to take A minus lambda. Lambda in this example was 2. So A minus 2i, let's just rewrite what that matrix was. That's actually this matrix right here. So here's the original matrix A. If I subtract 2 off of the main diagonal, we already did this. It's just this matrix right here. It's just that matrix right there. Now I need to be careful with one thing here. In this work that we're doing right now, we must work with A minus 2i, not the row echelon form of it. So some people are tempted to do that. Like, oh, well, this is the row echelon form, I'll just replace it with that. No, no, no. You must go back to the actual matrix A minus lambda I that you had calculated without doing the EROs. Okay? But what I'm going to do now, guys, is square that guy. Because I can see it in my box over there. I need to, the first item in the box says take A minus lambda I squared. So I need to do that. So let's just do -2, -2, 2, 2 times itself. You talk about coming full circle. Do you guys remember matrix multiplication? Way back to chapter 2, we have to do dot products of the rows of the matrix on the left with the columns of the matrix on the right, dotting them together. So let's just check this out, guys. If I do this, in this case, I have 4 minus 4. So if I go first row, first column, I have 4 minus 4. That would be 0. If I do the top right corner, I have 4 minus 4 again, which would also be 0. On the bottom row, I have -4 plus 4, which is 0. And then in the lower right corner, -4 plus 4, oh, it's also 0. Oh, we got all zeros. You know what? That makes our life much easier, because if A minus lambda I squared is the all 0 matrix, then condition number 1 on choosing the W1 is for sure going to be true no matter what W1 is. You can choose W1 to be anything, any vector. Any vector is going to be killed by this matrix. Creating a tornado up here. Right. Any vector is going to be killed by this matrix. So far, this is easy. This is an easy job. So what do I have to do, guys? I have to choose W1 so that it will survive this matrix. Should not become 0, 0. But it should not survive this matrix. And the fact of the matter is, nothing would ever survive this matrix. So the choice of W1 really comes back to here, choosing a W1 that will survive this matrix. Does anybody out there feel confident? There's many right answers, but can you think of a vector, a little column vector W1 here, that will not become 0, 0 when I multiply it by that matrix? pick something super easy. Now, 0, 0 is already killed. We don't want that one. That is easy. It's unfortunately, it's a little too easy. What's the next easiest thing? 1, 0. Yeah. Yeah, guys, if I do 1, 0 right here. If I do 1, 0, do you agree it's going to survive this matrix? Let's check it out. If I multiply by 1, 0, why am I doing that? Because my diagram tells me to do that. If I start with W1, I do A minus lambda I times W1 is going to give me W2. So if I want to know what W2 is, I have to take A minus lambda I, multiply it by W1 and see what I get. Well, guys, when you do this matrix multiplication, check it out. -2 plus nothing. So that's -2. And 2 plus nothing is 2. It's -2 too. Actually, it strips off the first column of the matrix. Did we ever talk about that? If I take some random matrix and if I multiply it by 1, 0, like what do you get? A plus 0, that's A. C plus 0, that's just C. Right, so if you take any matrix and you multiply it on the right by this standard basis vector 1, 0, you just pick off the first column. And that's what we got here. This is W2. W2 is the first column of A minus lambda I. You guys with me? By the way, I made some comment over here, didn't I? That W2 should be an eigenvector of A. Well, is it? Let's go back. We calculated the eigenvectors, didn't we? And we only came up with one eigenvector, it was this one. Right? So this was the eigenvector we calculated about 10 minutes ago. So is this an eigenvector? It's just a scalar multiple of this one. And a scalar multiple of an eigenvector is another eigenvector because they form a subspace. So they're going to be closed under scalar multiplication. That is an eigenvector. So guys, I can write down my x2 now. My x2 of t is going to be e to the 2t times w1 plus t times w2. Let's write it down and put a box around that one. Okay? That's my x2. So I'm just using this trial solution that we guessed. Somebody figured it out that this is going to work. We plugged it in and we figured out, yeah, it will work as long as we choose our W1 and W2 according to the diagram, basically. So that's what we did. And so we came up with our second solution. Now, at this point, we would probably want to stop and like do a Wronskian check. I gotta make sure that our X1 and our X2 are really Li, but we're not gonna do that. It's a little too tedious at this point. So I'm just going to tell you that they will be Li as long as you have chosen this trial solution. It will be Li. So it's good to go. James?
Over here.
Yeah.
It says A minus, is that 2i or lambda?
2i. Well, lambda is 2. So it could be whichever one you want, but I put the 2 there just because that is the lambda. Yeah, exactly. Okay, so what is the only thing left for me to do on this? Just enough room here. I just need to write down the final answer. I have 2 basis solutions, guys. So my final answer, in other words, the general solution on this example is x of t equals C1 times the first solution, which was e to the 2t times -1, 1, plus C2 times the second solution, which was e to the 2t times 1, 0, plus t times -2, 2. Go ahead and put a box around our final answer there. That's the whole thing. Some people have asked me in the past, you know, I've gotten this question before. People have said, okay, I chose my W1. I got my W2. I knew that it was going to be an eigenvector. Would it be okay? I get this question from time to time. Would it be okay to just go back and use the eigenvector that we had actually found in the first place, the V1 over there? And the answer is no, that is not okay. You actually have to live with the W2 as you found it, right? So we cannot just say, I'm just gonna cut this in half. You actually have to leave it as is. Even if it's not literally the V1 that we found over there, we have to live with -2, 2. Okay, so I'm gonna unerase that and just put -2, 2 here. Can you guys tell that I like this section? I really do enjoy this. Okay, so this is the defective linear system, and that's the W2. Feel okay about that? Now, I also will get the question, it comes up a lot, will this matrix here, when I square the A minus lambda I, will it always give me all zeros? And the answer is that for a 2 by 2 defective system, that is correct. It will always be the all zero matrix, which means choosing your W1 is a lot easier. Because you know that it'll get killed by this matrix. You just need it to survive this matrix. So that is true for a 2 by 2, but it's not true for larger matrices in general. Sometimes it will be true. But what I want to do now is show you a 3 by 3 case. Actually, so let me just tell you that for 9.5, for the section I'm kind of going over with you right now, we will only do 2 by 2 or 3 by 3 cases. I won't give you any matrices larger than that because it's another one of these things where ultimately you'd have to go put it onto a computer. Doing them by hand would be too difficult. It would just be too much. So I'm only going to give you 2 by 2s and 3 by 3s for this section.
Oh,
Yeah, please.
so if we didn't know what W1 to choose, is it always 1, 0? It could be different.
It's not always 1, 0 because what if A minus lambda I had a column of zeros here in the front? What if it looked like that? Well, now if I choose 1, 0 for W1, then when I calculate this, W2 would be all zeros and we don't want that, right? W2 should not be 0. We need to still be able to go one more arc before we get to 0. So you do have to be a little careful. Now, this is always the sticking point. How do you choose the W1? There's so many correct answers. The main correct answer is that it must survive this matrix. That's the key. Okay, but we're gonna practice more. We're gonna practice more. So I'm gonna go on to 3 by 3s, but before I do that, I would like to point out that in this section, we cannot see any complex numbers based on this restriction. So that whole Floyd thing we did on Tuesday, you're not gonna get that here. Do you know why? If it's defective, then the lambdas have to repeat, right? So if you had a complex eigenvalue, remember you always get them in pairs. Sorry. You always get them in pairs. And if it's defective, you have to have something being repeated, which means you have to get this pair repeated again. How many lambdas is that? 4 things on the board. And to have 4 lambdas, you have to have a 4 by 4 matrix to have 4 lambdas. So you're not going to have, so I'm not saying you can't get complex numbers in a defective system. I'm just saying that for Math 250B, you won't get that because I'm not going to ask you to do 4 by 4 matrices. And in order to have repeated complex roots, you actually have to have 1, 2, 3, 4 roots total. And you can't get that in a 3x3 matrix. So you won't see any complex numbers. Everybody can take a sigh of relief. In this section, there won't be any of those. There will be in 9.4 when we have the non-defective systems. You definitely will see them, but not in this section based on what I'm going to do here. This is going to be hard enough in just even the 3x3 case, and let me explain why. There are multiple ways that you can have a defective 3x3 system. So let's assume, I'm going to show them to you now. Let's assume that A is a 3x3 matrix. Defective. And if you've got room on your paper, you might sort of make 3 columns here. And I'm going to try to show this to you. Okay, so far so good. So I'm going to show you kind of the 3 possibilities. One way that A could be defective would be if you had a lambda 1 and then you had a lambda 2 that showed up twice. So there might have been a particular value of lambda and then another lambda. Of course, the first lambda, which is lambda 1, will give you V1. But then maybe this second lambda does not pull its weight and it only gives you a V2. That would be a scenario. So this is a 3x3 matrix, guys. You're supposed to come up with 3 eigenvectors. As you can see, this would be one way that might not happen. You could have a eigenvalue of weight 2 that only produces 1. Okay? What would be another scenario where you would be in a defective situation? Edgar? Oh, the same lambda 3 times. Yeah, how about that? Lambda, 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 right? And this has a weight of 3. Maybe together we only get a V1 and a V2. So this would be, again, we only got 2 eigenvectors even though the weight was 3. So it fails to pull its weight, so this is defective. Now I've made a 3rd column here because there must be a 3rd possibility. Does anybody want to try it? What's the other way that we could have a defective system here?
Zero matrix?
Actually, the 0 matrix is, believe it or not, is not defective. The 0 matrix is, in that sense, is actually a good matrix. So you have the lambda is just always 0, and it pulls its weight, actually. Check that out. So it's a little bit interesting. The 0 matrix is bad in terms of being invertible, but it's actually okay as far as being non-defective. But just in terms of like setting up, what other combinations of like lambdas could you have? So I have one lambda here that came up 3 times and produced 2 eigenvectors. What else could happen that would be even worse than that?
3 of them only could be 1.
Where's that coming from? The same lambda 3 times, but only 1 eigenvector being produced. Exactly, that's even worse. That is even worse. You just get 1 eigenvector. This thing is what I call super defective. Let's actually write that down. This is going to be the super defective case. Super defective. Okay. And by the way, guys, I'm going to need to keep these columns going a little longer. So I hope you're giving yourself room to kind of extend this even a little bit more. In a minute, I'm going to come fill that out. Before I do that, I have names for these others as well. The case on the left, where I have 2 different lambdas, I like to call this one the mixed eigenvalue case. So that's a defective system that's mixed eigenvalue. And the one in the middle, I don't have a good name for it. So I just called it regular defective. So these are just kind of my names for them. I'm not trying to claim that this is standard, the whole world talks about things in these terms, but these are the ways that I like to discuss this. Okay, so for next Tuesday's exam, everybody needs to be able to do any one of these three cases. I am hoping by the end of today, I will have had a chance to show you an example of each case because there are differences in what happens in these three cases. Let me, if you don't mind, I'm gonna keep my 3 columns going here. And I would like to write down what the 3 solutions would be for my, remember, for a 3x3 system, you've got to have 3 basis solutions. So what are they gonna be? In the mixed eigenvalue case, my first solution, x1 of t, will be e to the lambda 1 t times v1. That eigenvalue pulled its weight, by the way. So no problem, just write down that solution. My second solution, well, I have my lambda 2 and my v2, so I can make another one of those standard solutions, e to the lambda 2 t times v2, no problem. And now to get my third solution, well, this is the x3 of t, and now guys, this is where we have to do the w stuff. So for this third solution, we would have e to the, it would still be lambda 2 of t, and this would be multiplied by w1 plus t times w2. So just in the way, same trial solution that we just explained on the 2x2 example, we would use that here. Okay? So that would be that. That's in the mixed eigenvalue case. What about the regular defective case? Again, I have to write down 3 solutions. So x1 of t, that'll just be e to the lambda t times v1. And for my second solution, it would just be e to the lambda t times v2. Okay, so here I am, same lambda, but I have a different eigenvector. This is where I sometimes see people trying to stack a t. You don't need to do that because the v1 and the v2 are already li, just as is. We don't have to like fudge our trial solution at all for that term. Okay, and then my third solution, which is x3 of t, you already know what's coming. This is going to be e to the lambda t times w1 plus t times w2. The same rules on w1 and w2 that we've already been explaining. So this diagram and this box is still your recipe for that. That is still how you do it. Okay? So I'm going to try to save my diagram and save my box because we're going to keep using this to get my x3 here. All right? Okay, so everybody ready to take a deep breath and do the super defective one? This is the one that freaks everybody out. So I have the same lambda 3 times, but I only got 1 eigenvector. So how am I going to get my 3 solutions? Well, my first solution, x1 of t, of course, that's an easy one. We just do e to the lambda t times v. We can do that very easily. The second solution, well, I already have to go to my w's, right? So I already go to my w's, e to the lambda t times w1 plus t times w2. I go to my w's right away on that solution. But now we see what the real issue is we still need a third solution. A third solution, and it's like, how do we get it? For a 3x3 defective system, we're looking for a third solution. Here it is. We create yet another trial solution. And let me write it down. E to the lambda t times, trust me, I was not the one who figured this out. I'm just, don't shoot the messenger. I'm just telling you what it is. It's W3 plus T times W4 plus T squared over 2 times W5. Oh my goodness. Where, and hopefully you have room to write this down, we have to explain how in the heck do we get W3, W4, and W5? Well, guess what? There is a diagram for it. Just like I have a diagram for the W1 and the W2, there is a diagram to do the W3, W4, W5. And I'm going to draw the diagram instead of a whole bunch of equations. I'm not going to do the derivation where we compare the non-t terms, and then we compare the t terms, and then we compare the t squared terms. I'm not going to do all that. I'm just going to show you what happens. What happens, guys, is that you have a dot for W3, and you choose that. And then we make an arc, which is labeled with A minus lambda I, that goes over to W4. And then we make another arc with A minus lambda I that then goes to W5. And then finally a third arc, also labeled with A minus lambda I, that finally becomes 0. So it is a macro version of the previous diagram. This time, I think I will put the equations here in the box, in a box as well. This time, the W3, it does need to become 0, but only after 3 powers of A minus lambda I have gone by, right? So everything is going to get jacked up by 1 extra power. So the conditions here are going to be A minus lambda I cubed of W3 should become 0. And the second condition is going to be that, well, if you only squared it, if you did A minus lambda I, if you did A minus lambda I squared of W3, that it's not yet 0. So I do not want W4 or W5 to be 0 yet. They all need to be non-zero vectors as you're going along. Okay, so I'm just going to give that one to you, and you guys can trust me, I hope, that the derivation is more or less the same as the one we did for the 2x2 system. Okay, so there's a little bit to learn here in this super defective case. Make sense? So it'll make more sense with an example, probably. So I'm going to let you guys tell me. I came prepared today to do an example of all 3 cases. And I think I have enough time to do all 3 cases, at least 2 of the cases. And I'm going to let you guys tell me which order you want me to do them in. Or maybe you don't care. So I'm ready. I think I'll do one example before we take a break, and then we'll come back and do another example. Which case do you want me to do first? Alex? Super defective? Okay, I'll do a super defective. You know what? It's kind of interesting. People look at this and their immediate reaction is, oh, the super defective case must be the worst case. It actually turns out that, in my opinion, this is the hardest one. The mixed eigenvalue case. And there is a reason for that. The reason for that is that in the super defective case, even though you do have a little bit more that you have to memorize, because you do have to memorize what the X3 is, it turns out that choosing these W's in the super defective case actually doesn't go so badly. It's actually easier than it is in the mixed eigenvalue case. I'm going to show you with my examples, I'm going to show you that. I do think the easiest case is the regular defective case. That case actually is probably the easiest one. But let's do, I'm gonna do I'll have time to do both. So we'll get it all done here. Let's do a super defective example, okay? Are we ready for this? You guys look semi-excited. Try not to look too excited out there. All right, so here's an example. Let's do this. Let's solve x prime equals a times x, where a is equal to, I'm going to give you the matrix here. We're going to do -1, 1, and 0. And then we're going to do -2, -3, and 1. And then 1 and 1 and -2. just to save a little bit of hassle and time, I'm gonna put as a hint over here. I'm gonna give you a hint that your first lambda is equal to -2 and your second lambda is equal to -2. I'm just gonna give that to you as a free hint, just to save some time. Now, technically, there should be 3 lambdas. Can somebody tell me what the third lambda would be? Has to also be -2, for 2 reasons. One is that I told you this is the super defective case. In the super defective case, the 3 lambdas are all the same. The other reason, if I didn't tell you that, you can use your fun facts about the eigenvalues. So if we add up the trace of the matrix, you add up the main diagonal, you get -1 plus -3 plus -2, which is -6. So the 3 lambdas together have to add up to -6. And we've got 2 of them here. So the third one has to make that work. And so this implies by the fun facts that lambda3 is also equal to -2. So let's just take my word for that, that I've got my lambdas all equal to -2. I might do that on the midterm too, just to give you the lambda. You can see what a nightmare you have if you get the lambdas wrong, which is what you do at the very beginning of the problem. If you don't get the lambdas right, then you're not even clear on what's going on here, right? You've got to get these lambdas right. So let's get into this solution. We have lambda equals -2, -2, -2. Let's find our null space. And to do that, I'm going to add 2 to the main diagonal of the matrix here. So it'll be 1, 1, 0, -2, -1, 0, and 1, 1, 0. I always know that I can cross off a row. For a 3x3 matrix, just to review for next Tuesday's test, for a 3x3 matrix, you cannot just willy-nilly cross off any row you want. You have to make sure that you're crossing off a row that is involved in a linear dependency. In other words, the way I like to think about it is whichever row I cross off, the other 2 rows should not be multiples of each other. So in this case, is that possible? You can see the first and third row are the same. You should be crossing one of those off. If you crossed off the middle row right now, then you would actually need to cross off 2 rows, and that would actually not be correct here.
How did you get 0 in the second row?
How did I do what?
Get it there.
Oh, by making a typo. That should have been a 1. Sorry, miscopied it, thank you. Every so often, I like to make a little mistake on purpose, just to see if anybody's paying attention. Right, so, anyway, that's the matrix I should have had. Now, I guess I need to do an ERO here to get this cleaned up a little bit, but this is the matrix, by the way. This is the matrix A minus lambda I, just so you know. That is the matrix A minus lambda I, but I'm gonna twiddle it over here to another matrix. So the first row, I have a good pivot in the top left corner. And I'm gonna take 2 times the first row and add it to the second row, and it'll become 0, 1, and 1. Of course, I've got my row of zeros on the bottom. Okay, so setting up Z as my free variable, right? So we do our usual thing here, X, Y, Z. Z is my free variable. So now I solve for Y using the middle equation, and it becomes -t. And then X plus Y should add up to 0. So X is just equal to T again. And when I bust out that T, I get my eigenvector, which is 1, -1, 1. And so sure enough, we have the same eigenvalue 3 times, but only got 1 eigenvector. So this is super defective. This is the super defective scenario. Okay, so let's talk about it. I gotta do this thing with the W1 and W2 like we were doing before, and then I also have to do this W3, W4, W5. Actually, in order to really do this full W3, W4, and W5, I'm going to need to calculate 1, 2, 3 powers of the matrix A minus lambda I. So here's A minus lambda I right here. Let's just write it here again. A plus 2I, that's A minus lambda I, is 1, 1, 0, -2, -1, 1, and 1, 1, 0. Remember, you cannot use the row reduced version of that matrix. You have to use the actual matrix. So we're not using this. We're going back to here again. Okay, now I have to square this matrix. So I'm going to find out pretty quick who can multiply matrices together. You have to be able to multiply this matrix by itself. Do you want me to go through that or just tell you what it is? Go through it. Let me go slow through this. So we're going to write it down twice. So if I square the matrix, I write it down 2 times side by side. Okay, so this is just A plus 2I times itself. I'm just going to multiply it out. So now I have a whole bunch of dot products that I have to calculate. And I'm just going to start doing, so I go across the rows of the first matrix and I dot those with the columns of the second matrix. This is our usual matrix multiplication scheme. So the first row dotted with the first column, that's 1 minus 2 plus 0. That adds up to -1. And then if I do the upper middle entry, I have 1 minus 1 plus 0. That cancels out to 0. Top right corner, we have a 0, a 1, and a 0. Add those together, you get 1. That's the first row. And then it turns out that the second row is very similar. So let's go to the left middle entry. -2 plus 2 plus 1, it's actually 1. And then the middle entry is -2 plus 1 plus 1, cancels out. And the right entry is 0 minus 1 plus 0. That's a -1. Okay. And I will let you check that the third row is the same as the first row, because you can kind of see that it has the same entries in it. So this will be -1, 0, and 1. Okay, so that's just the square of the matrix. Again, why do I need that? Because I'm going to be calculating W3, W4, and W5 in a minute. Okay. I even need to go another step further and cube the matrix. Because look what it says. When I choose W3, can you guys all read this? When I choose W3, the cube of the matrix should make it become 0. So I need to know what the cube of the matrix is in order to be able to decide that. So that still has to be done. This one, I am going to omit all the writing out the dot products, and I'm just going to tell you what it is. It is going to be, I'm going to put it right down here, guys. It turns out, and this is why I think the super defective case is actually not the hardest case, is because this one, just like in the 2x2 system, this always becomes all 0. Okay, so that's kind of nice. That's kind of nice. So, what that means, what that means is that when I'm choosing W3, it has to be killed by this matrix, but not by this one. Right? Well, everything is killed by this matrix. You take an all 0 matrix and put a vector next to it, boom, it'll become 0, 0, 0. So that makes choosing W3 a little easier. Anything will pass this matrix and will be killed by this matrix. So does somebody want to try I know I haven't talked about W1 and W2 yet, but I'm actually going to start with W3. So based on what I've said so far, I need a vector that would survive this one, but not this one. And nothing will survive this one. So I really want to focus here. Can somebody give me a vector that you know will survive this matrix? Do not make it too difficult. How about 1, 0, 0 again? Now, don't choose 0, 1, 0. 0, 1, 0 would have picked off the middle column. But 1, 0, 0 will pick off the first column. That is what you want to do. Let's choose 1, 0, 0 right there. That's my W3. Now, if I know that that's W3, then I can do W4. The diagram tells me how to get W4. What do we do to get W4? We simply take W3 and multiply it by A minus lambda I one time. You with me on the diagram here, guys? We just wrote down a W3. I now need to figure out why do I need to figure out W4? Well, it's right here. I need to figure it out for my solution. So I'm gonna figure out W4 by taking the W3 and multiplying it by A minus lambda I. Yeah, that's how we're gonna get it. Let's, well, I'm a little premature here. I need to actually take the matrix A minus lambda I, it's 1, 1, 0, -2, -1, 1, and 1, 1, 0, times W3, which was 1, 0, 0. And remember that what happens is that this calculation will pick off the first column of the matrix. Okay, so again, if I just had a random matrix, A, B, C, D, E, F, G, H, I, and I multiply it on the right by 1, 0, 0, as true as I'm standing here in front of you right now, what's gonna happen is this will pick off the first column. So that's your W4. Okay, so far so good? What about W5? How do I figure out what W5 is? Well, I can figure out W5 by taking W4 and multiplying it by A minus lambda I. Or I can do something else that's maybe easier. Instead of taking W4 and multiplying it by A minus lambda I, can I get to W5 a different way? Go back to W3 and do 2 powers of A minus lambda I. I've already calculated 2 powers of A minus lambda I. You know what? Either way is correct. You can take W4 and multiply it by this matrix, or you can take W3 and multiply it by this matrix. The diagram justifies that. If I start at W3 and I hop 2 times to the right, I'll land on W5. Or if I start at W4 and I hop only 1 step to the right, I'll end up at W5. The question is, which one's easier? It's easier to be working with this vector.
Yeah.
Because it's 1, 0, 0, right? As opposed to this thing, which isn't, I mean, it's not that you can't do it. Anybody could take this matrix and multiply it by that vector, I'm sure. But I can already see directly that W5 comes from the first column of the squared matrix, right? Because if you put 1, 0, 0 next to this thing, you'll get the first column again. Just the same, it's the same idea I was talking about here. So let's do it. Let's just put -1, 0, 1, 1, 0, -1, -1, 0, 1 times 1, 0, 0. So I'm taking W3, and this is gonna effectively hop to the right twice to give me W5, and it's the first column. -1, 1, and -1. That's W5. And remember that the very next time that I hop to the right, I would end up at 0. Which means that W5 is an eigenvector. In the same way that W2 was an eigenvector here. Remember? The last vector before you hop to 0 is an eigenvector. Because if you multiply 1 time by A minus lambda I and end up at 0, You must have had an eigenvector there. AV equals lambda V. Yeah. The last vector before you hop to 0 must be an eigenvector. Let's check it out. Did we come up with an eigenvector already? This one. And here's W5. You see the connection? They are basically the same. This one is just simply a minus sign away from this one. So this is actually confirmation that we've done something right. The fact that the W5 comes out as a multiple of the eigenvector, that should make us feel convinced that this is reasonable. So this is kind of interesting, guys. I've actually figured out the third solution. The third solution is e to the, oh, I never wrote down the first solution. Right here, I could have done that. Maybe I should go back. I'm so sorry. I'm having too much fun. X1 of t, what am I gonna do all summer? Okay, X1 of t, this is e to the lambda t times v. That should have been e to the negative 2t times the v, which was 1, negative 1, 1. I could have written that down 10 minutes ago. I could have done that right here, right? We already had everything we needed. We had the lambda value, we had the v. We could have written that solution down 10 minutes ago. Okay, but what I'm gonna do right now, guys, believe it or not, is I'm gonna skip to X3. And that's because I've already done W3, W4, and W5, which is what X3 is based off of. So how's that gonna look? E to the negative 2t times, and now I put W3, we chose it to be 1, 0, 0, plus t times W4, which was 1, negative 2, and 1, plus t squared over 2 times W5, which is negative 1, 1, and negative 1. And that's X3. So I'm being a little out of order here, and if you end up doing things a little out of order yourself, it's actually fine. It's actually fine, and that's because if you are good with how I did the W3, W4, W5 thing, I claim we already have W1 and W2. Because look at this diagram. Look at the W3, 4, 5 diagram as compared with the W1, W2 diagram. Do you see that if you just kind of ignore this first arc, the rest of this diagram just looks like a carbon copy of the one for W1 and W2. You know what you can do? You can do that. You can say, I am going to, the W4 is in the place where the W1 is, and the W5 is in the place where the W2 is, and you can actually reuse those vectors to make the X2 solution now. Right, so I'm gonna do that right here. I don't have a huge amount of room. I'm gonna squeeze it right here. X2 of t is e to the negative 2t times, and now I've got W1, which was the same as W4, 1, negative 2, 1, plus, oh, this is horrible, I don't have a room here. Let me try again. I'll write this a little bit more carefully. Here's X2 of t, e to the negative 2t times 1, negative 2, 1, plus t times W2, which is negative 1, 1, and negative 1. That's the second solution. So I did the third solution before the second solution, but it works out fine. And then my final answer for the general solution, let's just put it here on the bottom of this side. The general solution, guys, and then we're going to take a break. The general solution becomes x of t equals, and on the 2x2 example I did a while ago, I wrote everything out again. If you would like to be a little bit more expeditious with it, you can just do what I'm going to do right here, which is you can write C1 times x1 of t plus C2 times x2 of t plus C3 times x3 of t. You can just leave it at that. you can just leave it at that. You don't need to recopy all of these boxes back into the answer again. We've seen that before where I sort of said, yeah, there's no need to write it down twice. It's good enough. So that would be it. That would be the final answer. So this is an example of the super defective case. Let me again reiterate that what makes it a little challenging is you have to remember the formula for the X3, which you will not need in either of the other two cases. So there's a little extra upfront learning you have to do, but the upside of it is that this matrix here is always going to be all zeros. It's going to really help in choosing the W3. And the other upside is that once you've kind of thought about W3, 4, and 5, you can recycle the W4 and W5 and use them as W1 and W2 very quickly to get the answer. Yeah. So, questions? Far so good. Oh my gosh, is it 5:30?
Yeah.
Oh, okay. Let's take a break for about 5 minutes, and then I'm going to come show you a mixed eigenvalue case. I need a break. I'm going to take it'll take me 5 minutes to erase this. So go ahead and take a quick break if you'd like, and then I'm going to show you an example of this mixed eigenvalue case, and then we'll be done. I thought I was talking a little slowly. All right. Sorry about that. 5-minute break.
I would go over it. You say this one might not be the part. And objectively, conversation. Get a little algorithm. There's a lot of. Yes.
You understand the diagram?
Yeah, because the last example, they was 16.
Yeah, if you overlay this diagram on top of this one, right? That you'll have this extra arc that would end up over here. But the rest of this diagram, starting from here, looks the same shape as this one, so you're just laying it on top. Okay. Yeah, that's what I was trying to say. Thank you. Yeah, sure, no worries. I'm trying to get this clock fixed because that's part of my problem. I can't tell what time it is half the time. It's always 11:45 in here. Oh, well. What's that? Oh, okay. I thought you were asking me a question.
Yeah.
Yeah.
Would be too late. Whereas, and then it's like. that one. I like short. I think.
No, well, it's like.
Mhm.
Oh,
Yeah, you'll get your. You'll get your.
You look like you're about to fall
Here, because.
back. Is it okay?
Yeah. I kind of think. I don't know if I can. Yes, there's. I always get that. I always get it. Oh, yeah. Mhm.
Yeah, it's gonna die. Next week, interesting.
What I do.
Really?
It's not.
I don't wanna say like,
I
it's
just
not
not-
your hair. But.
I don't like so.
It's
a meeting.
A minus 9 value.
And then they'll.
In
So it's just a word.
That's a perk. That's a perk of the third case. The other case. As we're gonna see. This one, we won't need to worry about the W345, but we will have. Right, right, that's gonna be an issue. Yeah, so we'll see, we'll see.
No, I. Not good.
What? My bad.
So like, I need.
Oh, no, what?
Everyone is.
Yeah. Wait, you gotta.
I know. They're like,
Well,
"Careful."
it's not looking
Careful.
Let's see, what's.
Like it's.
What we got? Alright, guys, it's been about 7 minutes anyway. I gave you a little bit of a short break today, but that's because I do want to do one more example. And I'm gonna go a little faster on this one, I promise. I think I was dragging a bit on the first example. If you have questions on this next homework assignment that you're working on, I probably won't get time for a lot of that today. I imagine most of the people have not gotten that far on it. So feel free to come back down to my office hours, either in Zoom or in person tonight. And check your email, because as soon as I figure out my plans, I'm gonna have some office hours for you tomorrow and or Saturday, probably almost for sure tomorrow, and probably on Saturday as well. So you may have some questions, and I don't want you to hold back. This is definitely gonna be on Tuesday's test. But let's do one more example today, guys, of this. I'm gonna do the mixed eigenvalue case. So I just did the super defective case. This is actually the one that I think is the hardest case. Even though for the mixed eigenvalue case, we don't have to deal with W3, 4, and 5. Okay, but let's see what we do have to deal with. Here's my system. So I have another 3x3 matrix. Remember, I promised I won't give you anything larger than a 3x3. And again, just because I don't want to spend forever on this, I'm just going to tell you what these lambdas are. Now, this one has enough zeros in it that we ought to be able to get them. Okay, if you wanted to, we could work them out, but I will tell you what they are. Turns out that the lambdas are 1, 2, and 2. We can check that, but I will leave that for you. Okay. And so I'm gonna go into each of my lambdas now and figure out what I can. So I'll just start with the easy one. Lambda equals 1. For this, we have a null space that we have to calculate. And quick reminder, we're just going to subtract 1 off of the main diagonal of A. So that means I'm going to end up with a 1, a -5, a 0. On the second row, 0, 1, 0. And the third row is -1, 4, and 0. So I've just subtracted 1 off of the main diagonal. And I know that this matrix is not invertible. Have to be able to cross off a row. I'll cross off the third row and circle 2 pivots in the first 2 rows. Okay. I've got my XYZ here set up, ready to go. In this case, Z is still a free variable. There's no pivot in the Z column. But from the second row, I can see that Y equals 0. So 1 times Y is 0. And then from the first row, X minus 5Y is 0. But Y is already 0, so this means X is also 0. And so I get my vector, I'll call it V1. When I bust out that T, I just have 0, 0, and 1 right there. And so this time I will write down the first solution immediately. X1 of T is e to the T times the vector 0, 0, 1. So there's your first solution right there. Okay, so far, so good. Question so far? That's just the first eigenvalue. So far, I actually don't even know if this is defective yet. I haven't actually worked on the repeated eigenvalue, but that's what I'm going to do next. So let's go to the other lambda. Lambda equals 2. Again, we have to do another null space now. This time I have to subtract 2 from the main diagonal of A. So if I subtract 2, I'll get 0, -5, and 0. And then 0, 0, 0. And then -1, 4, and -1. So I just subtract 2 off of that main diagonal. I have to cross off a row. Unfortunately, in this case, we have to choose the all 0 row. It's already all zeroed out. And in this case, I might just put the bottom row up at the top, and I'll do that with a minus sign change as well. And then the middle row, I can multiply through by -1/5. And the bottom row is all 0. So this is just a quick little ERO thing. Again, I won't spend a lot of time on that. That's what you're going to end up with right there. And if I set up my X, Y, and Z corresponding to these columns again, once more, I see that Z is free. There's no pivot in the third column, so Z is equal to T. And from the middle row, again, I get Y equals 0. And if I now look at the top equation tells me that X minus 4Y plus Z equals 0. The Y is already 0, so I can kind of ignore the middle term. It's really just X plus Z adds up to 0. And so if Z is equal to T, X needs to be -T. And if I bust out my variable on that, I'll get my second eigenvector here. I'll call it V2. When I bust out my T, this time I get -1, 0, and 1. So it's similar to what we did with the other eigenvalue, but a little bit different. And again, I'm going to go ahead and write down my second solution now, X2 of T, which is equal to e to the power of 2t times the vector -1, 0, and 1. Go ahead and put a box around that as well. Okay, I hope I'm not going too fast, but I'm kind of streamlining some of the calculations here. Some of the chapter 7 stuff, I'm just kind of gliding over it fairly quickly. But we can see that this is a defective system because the eigenvalue lambda equals 2 shows up twice, and we only got one eigenvector here. Yeah, so we are in the mixed eigenvalue defective case. So this is mixed eigenvalue. By the way, in my YouTube, I have an example of all 3 cases with some different matrices. So if what you're seeing today is not enough, you want to, I want to see another example, we don't have enough class time for that, well, you can watch a video of any of these cases. Those are in the Canvas page. If you go down to the additional videos, there's a link for that. you can scroll down to section 9.5 and you'll see that I put some of these together for you. Anyway, I do think that this is maybe the trickiest case in some situations, and I'm about to show you why. For this case, we only need the basic diagram, the W1, W2, and 0 diagram. And so I only need to calculate the first two powers of A minus lambda I. By the way, this is my A minus lambda I right here, A minus 2I. So let's just figure this out. A minus 2I is, I'm just gonna recopy the matrix just because I don't like to confuse myself with everything all over the place. So I'm just gonna recopy A minus 2I right there. Again, not to sound like a broken record, but you cannot use the row echelon form version of it. You have to use the matrix itself before you did any tweaks to it at all. Everybody with me? Now I'm gonna square this matrix. Why am I squaring it? Well, because in my diagram, this is the diagram, maybe I should just recopy the diagram. In my diagram, I have to do A minus lambda I twice, right? To get all of the steps of the diagram. So W1, W2, and then 0. So I'm gonna have to do two arcs here. So I have to square this guy. And again, this is, I'm gonna save a little time. I'm not going to, I think one reason I spent so long on that other example was I was going really slow on this calculation. Everybody's gotta be able to square a matrix in Math 250B by the end of the semester. If that's not happening, I'm not happy. So you gotta be able to square this matrix. So what you're going to get if you do it, because I did it already, here's what you're going to get. 0, 0, 0, 0, 0, 0, and 1, 1, 1. You can check that. If you need practice with matrix multiplication, you can check that. I don't have to do the cube of the matrix because the cube was only needed on the big diagram for W3, 4, and 5. So this is all that I need. But I have to now choose W1. I have to choose W1 to survive this matrix, but not this one. Now, in the example we did a few minutes ago, you remember I just said, well, let's just choose 1, 0, 0. Right? So if I do that, hold that thought. If I try to use 1, 0, 0 right here, remember, this vector is supposed to get killed by this matrix. Two powers of the matrix should kill my vector. Does this vector get killed? No, because it picks off the first column. Does this vector get killed? No, because it picks off the second column. Does this vector get killed? No, because it picks off the third column. None of the columns here are all zeros. And that's a difference. The super defective case, the whole matrix was all zeros, so it was easy to pick W3. But here, picking W1 is a little bit trickier. Can somebody think of a vector that would work? We can't use the three obvious ones. We can't use 1, 0, 0 here. We can't. Sometimes you'll be able to. Sometimes you can't. Even in this case, sometimes you will. If there's a column of all zeros, go for it. Right? Pick your W based on, you know, a standard basis vector lined up to that column. But in this example, I picked this one on purpose to show you that sometimes you cannot get away with a standard vector as your W1. Can somebody see something that would work just by kind of eyeballing it, doing a little mental calculation? Can you see a vector? Can you see sort of some numbers to put in here that when you do this multiplication, you will get 0, 0, 0? -1, 1, and 0. I think that is a good choice. Let's check it. If I put -1, 1, and 0 here, obviously the first row is all 0. Second row, all 0. The third row, I have -1 + 1 + 0. It works. Thank you, Anthony. That saves the day. That's not the only right answer. Actually, anything where these three numbers all add up to 0 would have been fine. Because this bottom row really just gives you A + B + C. Yeah, so anyway, that would be a good choice for W1. And then we have to figure out W2 from that. Remember, W2, we do not get to choose. We can choose W1, but now W2 is dictated by this diagram. So to get W2, I have to put, by the way, I should have been a little more careful. I also need to make sure that when I put my W1 here, that I don't get 0, 0, 0. So I do need to get, so here we do get 0, 0, 0. That's good, but down here, we don't want to get 0, 0, 0. Let's work this out, guys. I gotta do matrix multiplication here. 0 minus 5 plus 0. That's -5. Second row is obviously all 0. And the third row, I have a 1 plus a 4 plus a 0. That adds up to 5. So my W2, which is just A minus 2I times W1, is going to be -5, 0, and 5. For W2. Is anybody checking what our original eigenvector was in this case? This was the original eigenvector. We always want to kind of make sure the last W that we get should always be an eigenvector. Based on this one being an eigenvector, I feel pretty good that this one is an eigenvector too, because it is literally just a scalar multiple of the eigenvector that we got before. That should make us feel a little confident in our W2. All right, so now let's write it down. The third solution, x3 of t, is e to the 2t times, now I put W1, which was -1, 1, and 0, plus t times W2, which is -5, 0, and 5. This would be the x3. This would be the x3. And so the general solution, it's actually just this again. I should write it down again, since you guys are, some of you are taking notes on an iPad. You ought to be able to just like, copy, paste it, and put it over on the end of your notes, right? But if it was me, I'd still be sitting there with a pencil and paper, trust me. So I'm gonna write it down, how it would look, right? So the final answer for the general solution . You guys like the technology and all this good stuff? Some of you are still using pencil and paper. That's my way of doing it. I just got an email from the university. They said, oh, you've been doing Zoom recordings since 2020. And the university's paying for this Zoom storage of all your videos. So I get this email telling me, you need, by May 20th, I forget what the date was, by May 20th, right in the middle of finals, of course. By May 20th, you need to put all your lectures from the past 5 years into Dropbox. And I'm like, oh my God. Every one of these lectures is like some big, 2-hour file or whatever. And I've got probably 300 of them. This is why I don't like technology. It's like worse than cleaning my house. I would rather do that than try to clean up my files. My storage files. Anyway, sorry, I'll get off of my gripe session here. C1 x1 plus C2 times x2 plus C3 times x3. They always pick the worst time. Make us do stuff. So there's the x of t. Maybe the money they're saving on the storage, then they can, I don't know, help out with something else on the campus. Hopefully the money will go to a good cause. But that's the general solution. What do you guys think? Does it make sense? The case I didn't do here today is the regular defective case, but it's the easiest case. So I will let you either watch a video on it or just do it. It's not that hard. It's the same process. Choose W1, choose W2, and go from there. Guys, study hard. Stop by and see me if you have questions on anything. I'll let you go. Have a great rest of your week. Don't forget the extra credit quiz is due tonight. 3 points for your midterm.
I'm doing it.
Yeah, I guess.